and Dr. Merrick, and in addition to the rest of the crew here on this. So we have a little bit of an update, just the disclosures of the research report we have. I always like to kind of start off these talks of kind of where we started from what we know about Chiari malformation. I always find it interesting to kind of look back to this original publication by Hans Chiari's Austrian pathologist who described these congenital high-grade formations. This down here was the original manuscript. It was not in English, but translated, it says, about changes in the cerebellum as a result of hydrocephaly of the cerebrum. And that was kind of where this initial description of tonsillar ectopia came from and what came to bear Hans Chiari's name. The initial description had a couple of numbered variations, 1, 2, 3, 4, and subsequently a few other variations that were described, 0, 1.5, 3.5, and etc. really. But these are what came to be. This Chiari malformation type 1 is the focus of our study, described as ectopic position of the cerebellar tonsils, something that has a high prevalence in young age, but is prevalent, but occurs throughout all lifespan. Its formal testing suggests that there's impact on cognition beyond what you might anticipate from what you might classically think of the cerebellum. And that was something that really drove us with this project to kind of look beyond sort of classical thinking of symptoms of Chiari malformation as we were looking to redefine what a Chiari malformation is. So classically, this degree of tonsillar ectopia is what's usually measured. It doesn't seem to be all that well correlated with the impact of disease or outcomes of surgery or a variety of other things. It's probably one piece of the puzzle, and we set out to find out what the rest of those pieces of the puzzle might be. One of the ways I like to think about this is I like to pick on Dr. Librick's study, the PRA Severity Index, as well as a couple other studies from other institutions. And one of these studies, the conclusion was really interesting. It's that previously published algorithms failed to provide a prediction value with regard to clinically meaningful improvement following suboccipital decompression in adult Chiari patients. Future models and practical scoring systems are still required to improve our decision-making process. And that really speaks to kind of where we are with Chiari malformations. It's really difficult to predict who's going to be symptomatic from this anatomic abnormality, who's going to benefit from surgical intervention, and how to put all the pieces of the puzzle together. So again, I like the way this particular manuscript ended its title with "Can we do better?" Of course, we think we can do better. So one way to start is to start relatively simple. From our side, with this project, we're focusing on advanced imaging, but we want to better define some of these anatomic features with advanced imaging analysis. We started with a simple project. This is something that Dr. Haller and I have been working on recently, along with the rest of the group. Was the use of silver imaging to better define the effect of a Chiari malformation on the fourth ventricle. This goes a little bit to the idea of, is Chiari malformation a problem of a large cerebellum, a small posterior fossa? Is it something with obstructing CSF outflow, speaking to maybe that hydrocephalus as implied, I guess, by Hans Chiari's first manuscript? If it's a large cerebellum and a small posterior fossa, you might hypothesize a small fourth ventricle as well. If this is obstruction of CSF flow out of the foramen magnum, maybe that's causing things to back up. You might expect that fourth ventricle to enlarge. The existing literature is mixed. There are reports from mostly single institution retrospective studies that suggest it's smaller, some that suggest it's larger. So our proposal was to not just repeat the same thing and have yet another study that didn't finally answer the question, but to answer this question in a more robust method. So we leveraged large amounts of data from a couple different sources. Of course, the Redefining Chiari project that we're reading here, the part reuse study, as you've heard about from Dr. Librick, and the adolescent brain cognitive development study, the EBCD study. This is a fascinating study that's been carried out over multiple institutions around the country. It's looking at adolescents, but it's imaging about 12,000 kids and longitudinally repeating those images. And the goal of that study was to recruit typically developing individuals that did not have a neurological diagnosis. But if you recruit 12,000 of those, you're going to find someone with a Chiari malformation. And that's what we saw in the study. So we picked out those individuals and looked at how that Chiari malformation affected their fourth ventricle. At this point, there's 3 years of imaging available. This again every other year, so in baseline year 2 and year 4. And if you look at those incidental Chiari malformations in that study and do some fancy segmentation to kind of automate the volume of that fourth ventricle, you could see a really strong signal that the individuals with a QR malformation were much smaller than their controls. There's a large number of controls, about 11,000 once you remove the 71 or so that had a QR malformation, which meant that you were able to reach some really high statistical significance numbers. And if you repeated those over the years, as you can see when you get to year 2 and year 4, it was a consistent finding. In year 4, you had fewer of the individual's image at the time of this data release. The data was released in somewhat kind of a rolling fashion. But even with a relatively smaller number of control, still highly significant finding in this data set. But again, we said we weren't going to do just what was already done with literature, look at one data set and move on. We wanted to prove that this was replicable and reproducible for a more robust finding. So first, we reproduced it with the ABCD data itself, meaning we used the same imaging, but a different tool to do the segmentation. We wanted to make sure that this wasn't some artifact of the tool itself. The first version used FreeSurfer, which is part of the standard ABCD processing pipeline. Here we use a separate tool called DL Direct. This leverages some machine learning for AI approach segmentation. And again, with the same ABCD data, but a different method, we reproduce this result showing that it was robust to the type of segmentation that we were using. The other benefit of this tool is it's much, much faster than FreeSurfer. This is, of course, one of the benefits that machine learning oftentimes gives us, is it can implement things that typically take a very, very long time to do much quicker. So we then use that tool to replicate it in a separate data set, going off of the ABCD, no longer a very uniform cohort of 9 to 10-year-olds, but now using a local clinical cohort here from WashU. And again, even though it's a much more heterogeneous imaging cohort, the result still stood very well. And finally, we used data from the multi-institutional Part-Rees cohort. It's not just the data here, not just data from BBC, but data from multiple institutions that have all collaborated with the Part-Rees cohort, and again, showed that the results stood up very strongly. So this wasn't just one institution with a single retrospective cohort. This was multiple institutions, multiple different cohorts, multiple modalities, showing that the finding was quite robust. This was another one that I got, we're working on with the Redefining Keyword project, is showing how not only the static imaging features of QR malformation might have an impact, but some of the more dynamic features. So on the left, most classically, we're looking at a single image in time of what the tonsils look like when they're ectopic below the foramen magnum. And over on the right is a more dynamic picture. It's that if you were imagining taking that same image, but repeating it over time, watching it with the cardiac cycle. And this is one of those features we talk about a lot, is how those tonsils are pulsing away much more so than the rest of the brain. We sometimes refer to this as hyperpulsatile. One of the ways that manifests in this imaging technique we're using now is in this T2 weighted image with a few special features that go along with it. This T2 weighted image shows essentially an artifact whenever there's things that are moving quickly. So in some places, that's the CSF flowing, where you see this kind of dark signal, but there's normal CSF. But in the case of an individual with a QR malformation, hyperpulsatile tonsils, you actually get a very large black spot over the tonsils. And again, to one person, that might be an error, something that you don't want in the imaging. There is a way to correct that if you want a T2-weighted image without that artifact. But we took advantage of it as a feature because now we see in 3 dimensions what that artifact is. This is the corresponding T1-weighted image, just like you saw before. And what's interesting about that is that artifact shows us the hyperpulsatility. And once somebody has been treated for a QR malformation, this individual had a posterior fossa decompression with a germplasty. You can see that hyperpulsatility and associated artifact completely goes away. This particular patient had a fantastic result. He was my patient, so I know that that's the case, but it's just one individual. All of these images were required in our Redefining QR study, and so we'll have a lot more data on what that really translates to as time goes on, because we're currently recruiting for all of those. And finally, the thing I wanted to kind of quickly talk about, this isn't any kind of definitive data with long-term results yet, because it's we're currently recruiting and collecting this data. But the question that I get really passionate about is what can we learn about the functional impact from this anatomic abnormality? So this is where I get to functional MRI, and more specifically resting state functional MRI. One of the ways that I like to describe this is from a review paper here by Anish Mitra, who did his PhD here with Arm Brakel. And the way we describe this is if we look at a signal from the brain that correlates with our blood flow, If we pick two regions of the brain, it's kind of light blue and dark blue signal here, or circles here, and record the signal from those areas, you get a tracing that looks like this. And you can see those two the lines overlap quite well, meaning that they're highly correlated in time. And the interesting thing about that is if you look at any regions of the brain and look at their signal, if the regions of their brain are related, if they're doing some kind of common activity, if there's something about them that where they're working together, this bold signal that we're talking about is correlated in time. So that brings us to this idea of what's called resting state networks, where even at rest, when we're not necessarily doing anything in particular, laying in the MRI scanner without having to perform any complex task, all these different regions of our brain that are functionally related, their signals are correlated in time. And so we can pick out all the different voxels in the brain, do that same analysis, and it helps us draw these pictures of these resting state networks. It turns out this gets really complicated really fast. There's a lot of different ways you can define these networks, and there's just a small sampling of the multiple ways to define it. We typically end up here, or I personally end up using these two because these two people are here at WashU. Evan Borden and Matt Glasser has different ways that they have defined these networks. Most of what I use is actually the Gordon parcellation, but all these parcellations and many, many more have a lot of value. But what you'll see over here is this kind of inflated view of the brain, but this is all the cerebrum. And so you might ask yourself, aren't we here to talk about the cerebellum? And we are, but we're also talking about the entire brain, how all those affects intermingle. But that does bring us to the point of how are these networks defined in the cerebellum? Because that's not classically how resting state networks were defined. This was first described by Randy Buckner, who had previously been at WashU and moved on to MGH. And this is where he defined it a large group of individuals. And then Scott Merrick and Nico Dosenbach took it a step further to say not at a large group of individuals, but how do I define these networks for a single person? Because when we're treating people with chiari malformations, I'm not treating a group of 1,000 individuals all at the same time. I'm treating them one at a time. And so this was the kind of finding where we defined, or Scott Merrick and Nico Dosenbach were able to define these networks in the cerebellum at an individual subject level that brought us to the next level for this project. There's a few features about that, about how those networks are represented differently in the cerebellar cortex, and it's a deep dive to go into all those details, with just a few things to kind of help to tell us how motivated our study. Oops. So what we did first was we looked at these cerebellar networks in the ABCD study. Like I said, this was a fantastic source of about 71 individuals with chiari malformation, about 11,000 individuals that were our controls. It was an incidental finding about this, their chiari malformation itself, and a wide range as far as the severity of their tonsillotopia. Again, you can see some people here over 2.5 centimeters, and theoretically these people are at least subclinical. Maybe they have headaches, or maybe they have symptoms that hadn't yet top to a clinical diagnosis, but at the time they enrollment, they were not diagnosed with a chiari malformation. We looked at those various networks and how they might differ from individuals with a chiari malformation versus their controls, and the vast majority of them ended up having big differences in that default mode network. That default mode network were those two nodes that I showed you at the very first study. That was a network that Dr. Rapel has been become kind of famous for discovering and defining. And we see various ones where there's significant increases as well as significant decreases. They're not all involved in the default mode network. Some of them are between the default mode network and other networks like the singular-opercular network. This one, again, is another fan favorite right now. It's a topic of a lot of debate. This was one that Dr. Dosenbach has spent a lot of his time, even his PhD, studying this networking. It's kind of described, or it's initially described as the anatomic regions that were affected, the cingulum and the operculum, because they didn't really know what it did. More recently, this has been renamed, at least by Dr. Dosenbach's Revent and Mark Riegel's group, as the action mode network, as kind of the yin and the yang to the default mode network. It gives it a more functional name. It's the anatomic name, but it certainly makes a lot more sense as far as this yin and yang to the default mode network. And it's very interesting to me that we're finding those specific changes in that action mode network in individuals with chiari malformation. This was some of that preliminary analysis that's all being carried out right now in our redefining chiari study. And hopefully we'll replicate this with a much larger cohort, and more importantly, show how these respond to intervention for those people who have a treatment, and we'll study that before and after their surgery. That's gets me to where we're at with the redefining chiari study right now. The data collection is ongoing. It's going to be a combination of pediatric and adult, where again, like ABC data will all be pediatric, longitudinal before and after surgery. and correlating with all our standardized cognitive behavioral testing. The analysis and those results will follow.